In this video, we consider a stationary ADL model. We show how to derive the autocorrection model, and we give an interpretation of the ECM model. We consider the ADL11 model given by yt equal to constant plus theta yt minus 1 plus phi 0 xt plus phi 1 xt minus 1 plus an epsilon t. We make the usual assumptions. T goes from 1, 2, all the way to t, so that's our sample size. Epsilon t is IID with constant mean and variance. And finally, initial values are given. Moreover, we assume that xt is stationary and the parameter theta is numerically smaller than 1, which implies that yt is a stationary process. Recall that given stationarity, we could find the long-run solution as yt equal to constant term divided by 1 minus theta plus phi 0 plus phi 1 divided by 1 minus theta multiplied by xt. So the long-run solution defines the steady state. This is the equilibrium relationship for yt given xt. We could rewrite these coefficients, call them alpha and beta, so that the long-run solution yt equals alpha plus beta xt. We can rewrite the ADL11 model so that we directly incorporate the long-run solution, or in fact we incorporate the deviation from the long-run solution. So we can rewrite the model and see how yt is reacting whenever it is away from this long-run solution. So that's the idea of the so-called error correction model. So to derive the error correction model, what we do is simply add and subtract terms to the original ADL11 formulation. So first let's just rewrite the model like this. And now we want to reformulate it so that first on the left hand side, instead of the level of yt, we have a first difference. To do that, we simply subtract yt minus 1 from the left hand side, and we subtract it from the right hand side. So if we consider the first part, we get the change in yt, get the constant term, and then we have theta here minus 1 times yt minus 1. Now we also want to rewrite the x's over here so that we only have the lag level of x, and then we have a number of first differences. In this ADL11 model, we only get one first difference. The way we do that here is we rewrite xt into a first difference simply by subtracting phi 0 xt minus 1. And then we add the same term over here. So we are simply adding and subtracting terms. Then we can write this as phi 0, the first difference in xt, that's the first term here. And then we have phi 0 plus phi 1, xt minus 1. And finally we have an epsilon t from before. Note that the model we have here is identical to the ADL model we started with. So we can estimate the representation up here, or we can estimate the representation down here, and we get exactly the same results. We can go back and forth between them. We know what the parameters in one model are in terms of the other. Finally, let's just write this in the following way. We have the first difference of yt on the left hand side, and now we take the coefficient here in front of yt minus 1 outside of parentheses, and then we rewrite it as 1 minus theta with a minus in front, so that's identical to the parameter we had up here. And then we add a big parenthesis here. We have yt minus 1, that's the level, the lag level of yt. Then we take the constant term inside the parenthesis. We note that we now have this coefficient in front, so we divide through by that. That gives us minus delta divided by 1 minus theta. We do the same for the lag level of xt here. So we get minus phi 0 plus phi 1 divided by 1 minus theta, multiplied by the lag level of xt, like this. Then we had the other term here, the first difference, phi 0 first difference of xt, and finally we had an epsilon t. So this is the error correction model corresponding to the ADL 1.1 model. Note that the model here tells us that delta yt reacts to, and then let's look at what we have inside the parentheses here. First, we have a coefficient here which we could call alpha. That's the same coefficient as the one we had up here. It has a minus in front, but it's the same coefficient. The same here, we have beta. So note that what we have in here, inside the parentheses, this is the deviation of yt minus 1 from its long run equilibrium value given xt. So this is yt minus 1 minus alpha minus beta xt minus 1, like this. So this defines the deviation of yt minus 1 from its long run equilibrium value given by the long run solution that we have up here. So the ECM model here tells us that the change in yt is related to the deviation of yt from its long run equilibrium. What we have in front here is a coefficient gamma 1. And note that if theta is numerically smaller than 1, so that it's greater than minus 1 and smaller than 1, that implies that the coefficient gamma 1 must be greater than minus 2 and smaller than 0. To illustrate the idea of error correction, let's do a plot. We have t on the axis here, and this is 0. And let this be the deviation of yt from its long run solution. So the point we have here is yt minus 1 minus alpha minus beta xt minus 1. So in this case, this is above 0, which is the same as saying that yt minus 1 is above its long run solution. So for yt to error correct, we need the coefficient gamma, that's the coefficient we had here in front of the parentheses. We need gamma 1 to be negative so that the change in yt is negative, all else equal. So if this term we have here inside the parentheses, the entire term down here, if this is positive, it means that yt is above its long run solution, so it has to come down, which is equivalent to a negative coefficient down here. So if gamma 1 is negative, then yt, all else equal, will converge back towards its equilibrium. There's a force taking us back towards the long run equilibrium, so we can think of the long run solution as being an attractor for yt. Likewise, if we were below here, we would need yt to converge back, which would be the same saying that gamma 1 should be negative. So that's all for now. Thanks for watching.